All right, last but not least, okay? And this one, again, let's just use the same blocks here once again. All right, this time we've got a pulley system set up here, frictionless pulley, massless, stretchyless cord coming down this way. It's a good old 8 kilogram block here, 5 kilogram block here, tension here, tension going up here, 8 G's going down this way, and a frictional force, F of K. Frictional force opposing this motion down this table. Okay? All right, once again, the acceleration going this way is the same as the acceleration going this way. I didn't like the way Expert TA did this problem because they had an A1 and A2. It's the same acceleration because if we're just going to spread this out into a straight line. And so when we bring this guy up here like this A just comes with it, and so it's the same acceleration. So we're going to set it up the exact same way that we did the last one, except that this time we have a frictional force, mu of k. And let's just say, for argument's sake, mu of k is equal to 0.5, okay? And we know that the kinetic frictional force is defined as mu of k times the normal force. Now, we're giving ourselves a pretty easy normal force here because we know that mg is coming down here and normal force is coming up here, and that the only in the y direction on the 5 kilogram block, so we're just looking at the 5 kilogram block, the y direction is equal to 0 because it is not crashing through the table, it's not flying up in the air, and that would be Fn minus mg. So therefore, the normal force in this case is equal to mu of k, which is 0.5, times 5, times g. Okay? So we've already calculated the normal force. The frictional force, the kinetic frictional force, and it's going in the opposite direction. So let's just go ahead and put it in. We've already calculated it. This is the magnitude of it. So F of k is equal to 2.5 times 8, which would be 20 newtons. Pretty glib, huh? I'm double checking. Oh boy. So let's double check here. 0.5 times 5 times 8 is 20. That's what I thought. Okay, so that's equal to 20. That's the magnitude of it, 20 newtons. So let's just put it back in a train. Let's just do the exact same thing. Now, on your problem, we might look at it, I'm doing this on Monday afternoon. I know nobody's going to watch this between now and class tomorrow morning, but we'll probably do this in class tomorrow. So here's what we got. Let's build our train here. 5 kilograms, 20 newtons going this way, negative 20 newtons going this way, a tension going this way, a tension coming back this way. See, we took care of the, and this one doesn't have any friction because it's hanging, okay? And 8G going this way, 8 kilogram, 5 kilogram, and 8.0 times 9.8 going this way, all right? And then the whole system is accelerating that way. So let's take, once again, we're going to take sum of the forces in the x direction is equal to 5 plus 8, which is 13, times a, which we don't know, which is equal to, let's just add them up, minus 20. So it's a lot. So all we've done is we've just taken the Atwood's problem and added a force here is all we've done. So the acceleration is going to be a little bit slower than what we had in the Atwood's problem. Is equal to plus t minus t plus 8 times 9.8. Okay? All right. So now we've got 13a is equal to minus 20 plus 8 times 9.8. So let's just put in all the numbers here. So I've got minus 20 plus 8 times 9.8 over 13. There we go. That's my acceleration. And I know it's going to be positive because negative 20 is not near. I mean, this is almost 80. So I've got 20. That was 20 times, oh my gosh, 20. How about negative 20 plus 8 times 9.8 divided by 13? It's 4.49. Now again, to finish the problem, we'll just come over here. We'll just look at this block again. So I know that the sum of the forces in the x direction for the 5 kilogram block are equal to 5 times 4.49. And that is equal to minus 20 plus t. So the tension, that becomes pretty simple. 5 times 4.49 plus 20 is equal to the tension, and we're done. And that comes out to be 42.5 newtons. That's the tension in the rope. Easy peasy. Your homework problem, they make it a little bit harder because they really want you to work it out. So we might look at it once you've had a chance to look at it. Oh, there's the key from the problem. All right, out here.